It's about the normal distribution, and I'm sure all of you are familiar with this. So you've got these nice bell-shaped curves for a univariate normal distribution. So the reason why the normal is important is pretty much uniformly used in vision. Most vision problems in some way are formulated with normal distributions. A very common one is to assume that noise that you encounter in your measurements is normally distributed. So when you're applying additive Gaussian noise or additive noise to images, normally you would start off with something that's around the mean of 0, and then you would increase the standard deviation as you're adding more and more noise to your problem. So you're testing the numerical stability of your algorithm, for example, and you want to get really noisy images, and that's how you do it. You add normal distributed noise. So that's so that's with one variable, you get these nice bell curves. And we want to generalize it to more than one variable, because very often you have more than one variable that you're measuring or trying to estimate. And this is what it looks like for a multivariate normal. So you've got two parameters, or two types of parameters. One is mu, which is a vector determining the position of your distribution. Yeah. And the second one is, I guess, the more interesting one. That's a covariance matrix. Do you guys know about covariance matrices? Sort of, yeah. Anyway, they encapsulate the covariance, the shared variance between your different variables. So x here is a vector of the different variables you're looking at, and the covariance will be a d times d matrix, where d is the length of the vector. Two important things to note about the covariance matrix, or the form that it takes, is that one, it's positive definite, which means this. So for any real valued vector z, this has to be satisfied, right? And there are a bunch of other properties that positive definite matrices have. So you can look at those, because I don't know all of them. And the other thing is that it's symmetric. So do we know what a symmetric matrix is? Yeah. It just means that it's equal to the transpose. Yeah. So that's what it looks like. That's it. We can all get to lunch. Not quite. Three types of covariance matrices. Sorry.
So in this case, the covariance matrix would represent the covariance between all the data items.
Sort of, yeah. So.
And all the data items would be x, right?
Sorry.
All the data items would be x in this case.
Yeah. So x is a vector, and you would, for example, if you have a two-dimensional thing, you would have x1 and x2. Then for your means, or for your position of where the distribution is, you would have mu1 and mu2. So that's also a vector. And then you would have a 2x2 covariance matrix. Yeah. And the covariance so next slide. Covariance matrix has some special properties. So you have three types. The first one is spherical. So that's essentially a scalar value multiplied by the identity matrix. Yeah. And what it means is that your hello, welcome. Thank you. Nice of you to join. What it means is that essentially the variance in each variable is equal, right? So you end up with this circular kind of distribution. So the position of where it is determined by your mu, yeah, and how spread out it is determined by the magnitude of these values along the diagonal, yeah, and its shape is the kind of relative values with respect to each other. So in this case, it's spherical because both values are the same along the diagonal. Yeah. If the values are not the same along the diagonal, so you have each variable has different variance, or each of your x's has a different variance, and you end up with a diagonal covariance that has different values, and you end up with something that's ellipsoid or hyperellipsoid, if you like. Yeah, so if you're increasing the variance in your x1, then that will spread it this way, and if you increase it in x2, then it will spread it the other way, like at the top. Yeah? In this case, are x1 and x2 independent? We have a yes?
Yes.
A yes, unanimous, yes. What about in this case?
No.
No?
Yes.
Yeah.
Oh yeah.
Yeah? Yeah. What about in that case?
No.
No.
No. So, in this case, your matrix can have non-zero values anywhere in the matrix. But you've got to remember that it still needs to be symmetric, right? So in this case, the sigma 2,1 and the sigma 1,2 are actually, they have to be the same. Otherwise, it's not a symmetric matrix. Right? And in this case, what happens is you end up with something like this that actually can be stretched along any axis. I'm waving this pen around a bit. So, in the diagonal case, we already said they're independent, and I think we're going to show why. This was already. Oh no! Come on, that's mean. I've got these new marker pens, and I like the whiteboards, but it's all going to be shining everywhere, isn't it? Where's the best place to write? Just down here.
Control D. It turns the
You've done this before. Control V.
B.
B. Nice.
Stupid.
Yeah, it was.
We just dim the brightness.
Could do, but that's all really complicated. I can just write it here and then lift it up, and then if you can't see it, you can't see it. And I'll probably make a mistake anyway. So, so let's start with this thing, which hopefully I can copy out. Actually, we don't need to copy it out. Right? So we've got. So let's do it for a mean vector that's 0, yeah, because it's simpler that way. So your mean is 0, and the covariance matrix, let's do a diagonal matrix. Do you want it to be spherical or non-spherical? Just diagonal. Let's do diagonal.
Do both.
Do both. It's kind of the same. So what's the, if we're going to have this thing is equal to I've mixed a few deltas and sigmas. So what do we need? We need to know what the determinant of one of these is for the first term. Yeah? And then square root. And we need to know what the inverse is. So do we know what the determinant of a 2 by 2 matrix is?
Product of. Is it 0?
2 by 2 matrix. Determinant is 0. Always.
No, product is 0.
Diagonal, like
This diagonal minus this diagonal. Yeah?
yeah.
Alright. So your
I'm in the second part of the 0.
sorry?
2, 1 times 1, 2 will be 0.
Yeah. So it's a diagonal matrix, right? He's way ahead of the game. That's a 0. So you just end up with this term. So that goes in the front, and you're taking the square root. So you're on the square root of this, which is just Yeah, that's pretty easy. And then for the inverse, do we know what the inverse of a 2 by 2 matrix is?
Swallow the diagonal and negate the right diagonal.
1 over the determinant.
And then 1 over the determinant.
So you go 1 over the determinant multiplied by a matrix where you swap these two, and you swap these two, and you also add minuses.
You don't swap. No, you don't swap them. You just change their sign.
There's zero anyway.
They're zero anyway, so yeah, it doesn't matter. But
More complete.
you could be right. Well, they're the same as in the zero. Anyway, you end up with what? With the same term as this. So you end up with multiplied by a matrix that is these two swapped. So minus into squared. Do we add minuses?
No.
The zeros in there. And that's to the -1. Yeah. So when we do this multiplication, we end up with what? These two cancel out. So you end up with this to the -1. So 1 over this. Yeah. And the same with this term, but you end up with that. Does that make sense? Sort of? A little bit? Anyway, to save me writing all the rest of it, you can kind of see that you end up with this term here because you have a zero mean. Yeah, so you don't have anything being subtracted. So your mu is 0. You end up here. And then you get to here just by taking the inverse. Pretty straightforward. Yeah. And you end up with that. That term at the front. And then when you multiply it out, it actually turns out that you can separate it into 2. Can we see that? Or not? We need to do it.
No,
It's pretty straightforward, right? You can kind of. It's a really easy example. Just kind of. Just wanted to show that sometimes I get scared by these equations, and it's nice to see that they're not actually complicated. So you just you multiply out, and you end up with essentially showing that the two variables are independent when you have spherical or diagonal covariance matrices. Yeah. Not the case when you have a full covariance matrix. I see if I missed anything. Cool. So now we're looking at the full covariance matrix. And something you can notice earlier when I was saying that this side here is pretty much the same as these, but rotated around an axis. Yeah? And actually you can write this out a little bit more formally. So if you imagine a new coordinate frame, the green one, where you're priming the two x1 and x2, then you have essentially a diagonal matrix in that coordinate frame. Yeah? And then what you want to do is apply a 2D rotation to move the coordinate frame to the one that you're actually interested in. So kind of, if you think logically, then it means that you can express any covariance matrix as a diagonal matrix plus a rotation. And the rotation will give you the principal axes of your ellipse, essentially. So the direction in which the variances are spreading. Yeah. Let me see. Was I planning to prove this as well? Or not? Probably not. Yeah, we probably don't need to prove it, but
how do you compute R?
Good question. So if you have any covariance matrix and you want to compute R, and you know this, so you know that your full covariance matrix is equal to a rotation matrix times your diagonal matrix times another rotation matrix. You can use that to actually calculate R. So do we, I don't know, how good is your linear algebra? Do you remember anything about eigenvalues?
Decomposition.
Eigenvectors? Singular value decomposition. Yeah?
Yes.
So if you take the singular value decomposition of a full covariance matrix, so the SVD of a matrix is, if you have a matrix, but it's basically this will turn into a matrix U times, how do they normally denote it? Like this, times V transposed, where this is a matrix with a diagonal matrix with all the singular values in order. Yeah? This is a orthogonal matrix, and so is this. And because you have a symmetric matrix,
It's just the eigendecomposition.
sorry?
You don't need SVD because it's symmetrical, it's just the eigenvalue decomposition.
Yeah. So because it's symmetric, actually these two are the same as well. So you get a rotation. That's why you get your rotation matrix. So that's, I mean, I'm sure you can look at the book and find out more information about it, but that's generally the idea. So you can use SVD of the covariance matrix to estimate the diagonal matrix.
And this is how the higher dimensions as well.
Yeah. So this is, yeah, when we go further on and you see the notation in the notes, you know, instead of using these small ones, the notation changes and we're using large sigmas. And that's because each of these values doesn't have to be a scalar. They can be matrices themselves. So the way we're just looking at a partitioning of the problem, essentially. Anything else we want to say about this? Everyone okay with this?
First question that we did. Basically, we're interested in the in Monte Capital. We could obtain. I mean, is Lambda capital unique?
Yeah.
Couldn't we get another diagonal matrix that has not the eigenvalues in it, but other values, and is also diagonal?
No.
Thank you.
Unless someone has a different idea, not as far as I know. I think no. Let's just say no. So, you know that you can express a. Actually, why do you think it might be important to be able to do this? To be able to rotate the coordinate systems?
Because you can then decouple every normal distribution.
Okay, next thing is transformation of variables, but what happens here? Okay. So y equals ax plus b, what kind of a transformation is that? Yeah, linear.
No,
Sorry?
is there another name for it? Isn't linear just ax?
Well, what's the equation of a line?
Ax plus b, but like linear is when it passes over the sum, right? Like a times x plus y is ax plus ay.
following. I think it's linear. It's fair to say that this is a linear transformation. I think non-linear is when you start introducing powers and more complex stuff in a simplistic way. Yeah? No? You don't like the beat. You want to get rid of it.
Well, no, it's just that, you know, what they, in my algebra course, they had another name for that thing. Forget what it's called.
Okay, well, it is a linear transformation. I mean, you said affine. I guess affine is not, well, it is linear, but you can introduce shear and so on. So
Yeah, fine.
affine. Yeah, it's linear. So essentially, what you're saying is, if you have a probability distribution x, and that's a normal, yeah, and then you transform the variable where you want to find a new probability distribution of y, and that's a transformation, a linear transformation of x. If you plug everything in, you end up with this. So your new mean, the mean parameter for your y distribution is this, and then your new covariance matrix is that. Hello, you've missed all the fun bits, and now it's just downhill. In fact, it's just going up. Anyway, the important thing about this is, in practice, it's much easier to calculate, to sample from a distribution where the mean is 0 and the covariance is identity. So you can sample from that, and then you just use this transformation to go into your new distribution. So computationally, it's actually important.
Can we take that PRY as given?
Sorry?
So your Y transform version is a non-Y.
The y transform version is a known y.
No, that's fine. Can you show me mathematical operations to get from that to that?
To get from there to there.
Yeah.
Could do. We need to plug it all in to here, and then start working it on the board. Do you want to do it?
I don't know, I'm asking you. I want to make some notes.
Okay, well, we can give it a go. I don't know how long it will
I mean, are we
take.
expected to be able to do that? Is my question.
No, I don't think so.
Alright, we'll save that.
I don't know, it's up to Gabriel. He might ask you to do it, but I don't think so. I certainly don't think we're expected to show you how to do it on the board in class.
It's a part of discussion, isn't it?
Yeah, absolutely. But I think you can find it in any book. So I think the class is meant to give you a broad overview rather than derive everything. But we can do it. We can do it after, maybe. How about that?
Yeah, fine.
Yeah. Okay, so that's the transformation of variables. Then you've got marginal distributions. So you've already done marginalization. Yeah? So you've got the combined distribution of two variables, and you want to get the distribution of one of them. So essentially you integrate your combined with respect to the one that you're not interested in to get the distribution of the other. Yeah? And it turns out that for the normal it's quite simple, so you can actually just pick out, if you know that this is your covariance matrix, then you can pick out the partitioned terms. So you don't need to do the integral. It's just, this is a property of the normal distribution, just like this, and just like everything in this lecture. It's all normal distribution, right? So it means that if you partition it in two vectors, x1 and x2, then you can find the variance just by taking the upper left quadrant, so the upper diagonal of your matrix, of your original covariance matrix, and then you do the same for x2. And what does this essentially mean? why might that be important? Why might you be interested in that? So you've got this combined thing. Would you be interested in getting just one of them individually? Possibly. Basically, this tells you the distribution of x without any information about the other, right? So you're separating them. Might be useful, or it could be that you know lots of information about one, so you want to separate and find out what you don't know. Next property of the normal is conditional distributions. So if you know a lot about one of your variables, then how do you plug that information into your multivariate normal distribution? Well, again, like with the previous two examples, I don't want to be writing this on the board. Don't ask me. No. But it turns out that if you fix, so if you're interested in the probability of x1 given x2 is a particular value, then a property of the normal is that you can find this out directly from your mean and your covariance matrices. So in actual fact, what happens is that if you fix one of the values, then your mean is shifted with respect to the value that you fixed. Okay? So you see the mean of this distribution, depending on the value that you're fixing, depending on what value it takes, the mean of where the distribution is shifts. Yeah? You can see that easily because of this. But the new covariance, so the covariance of your new distribution given your assumption or your knowledge, that isn't dependent on the value that you fix. Yeah, so that stays the same irrespective of the value that you're fixing, or the knowledge that you're incorporating. Yeah? Does that make sense? Sort of? And what if we have, so this is a full covariance matrix. Yeah? What if it was just a diagonal? What would happen to the mean value of your new distributions or your conditional distributions?
Be the same.
Right.
So it would be 0.
Because this term is 0. Yeah. So the mean will stay the same, stay in the same place. What would this be?
Sigma 1.
Yeah. So you just take the part of the covariance matrix that represents your variable. Yeah. Because the variable is independent. So it kind of makes sense. And the rest of the values are 0 anyway. And obviously it's exactly the same for the other variable that you may choose. Is that okay?
You read the last few lines again,
From back from basics.
I was just
Sorry?
You're joshing with me.
No. I mean, I think it makes sense when you consider what these values can take. So when you have spherical and diagonal matrices, they just cancel out, so that doesn't move. Yeah.
So, can I ask you a question on not this
Sure.
slide, the slide
No,
before?
no more questions.
On margin.
After him, that's it. Go.
On marginals, on the slide before.
Yeah.
If they're not independent, x1 and x2 are independent, does that mean that does that mean like PR of x2, the marginal won't sum to 1? Like the integral of that? Because it doesn't give you all the information about the...
Right, in this case, are they independent? In this case?
Well, no, they're dependent in this case, right?
Yeah.
So does that have any impact on the marginal distribution that you find?
No, I don't think, no.
Okay.
The marginal distribution separates them, right? So you're doing the integral.
But are you losing some information like, when you do that?
Well, you're discarding the information that the other variable contributes to your.
Because to get back to the full probability, you can't just times them back together, right?
When we go back to the full probability. Sorry, where? Where am I going?
No, I just mean here, like if you at the bottom, probability of x, which is the whole graph, equals probability of a function of x1 and x2. And if they were independent, then you can split them to probability of x1 times probability of x2. Is that right?
If they're independent.
Yeah.
Yeah.
But in this case, they're dependent.
Yeah.
So does that have any impact on the graph? That's what I'm saying.
On the graph.
On the marginal distribution.
No, this is just whether they're dependent or not. This is just what you end up with.
Okay.
I don't really.
Well, I mean.
So this is the full case. This is the most complex it can be.
Okay.
The others are all just simplifications of it. So when they're independent, it's. I mean, you know that this would be that anyway because you can separate them individually, and the multivariate is just a multiplication of the two.
Okay.
Yeah.
Mm-hmm.
So this is the only case that doing marginalization is interesting because otherwise you kind of have it already.
Yeah.
Yeah.
Okay.
Sorry, it took me a while to. Okay. So this is, I guess this is what we're saying, that if given these equations, if you have a diagonal or a spherical matrix, then the way that the mean shifts is different. So in fact, the mean doesn't shift; it stays the same. Yeah, and your covariance remains the same as for what it was for the variable in the first place. Product of two normals. So here you're just going to have to take my word for it because it's horrible. It turns out that if you multiply two normal distributions together, you end up with another normal distribution with a constant in front. Yeah, it's just another property of the normal distribution. And the new parameters are these lovely equations. Yeah. What does this remind you of? You know, yesterday we were multiplying, I don't know, categorical with the Dirichlet. Why were we doing that? Because they are conjugates, right? So does it look familiar in any way? That you multiply two distributions together and you end up with something of the same form as one of the distributions and a constant in front.
When they are conjugates?
Sorry?
When you have to do?
Yeah, when you have conjugates, yeah. But here you're multiplying two normals. So actually the normal distribution has a nice property where it can have self-conjugacy around the mean. So there's some special property about the mean.
Could just ask, what does the constant has the form of a normal mean? Don't understand that. But if it's a constant, or is it a function?
X is A, right?
So it's not.
It's not how you calculate the
Yeah.
constant.
So it's not. It's a normal, but in the mean, and not in your variables. Yeah.
Yeah.
Sort of. I don't know. The graph is nice. You see that the mean ends up in the middle. Sort of. And then. The property is that the mean ends up in the middle, so it's split between the two, and the variance actually becomes much lower than both. But this is just given. I mean, I think nobody would ask you to prove this. Important to know for the exam. this one is, I guess, the most difficult to visualize. If somebody can explain it to me, that would be nice. It basically means that, I need to look at the notes because I always forget this. So you're considering a normal distribution whose parameters, whose mean is a function of another variable, right? So your normal distribution of x is actually a function of y, and that has a property where again you end up with a constant and a different, like a transformed normal distribution in the variable y. And apparently you should be able to visualize this very easily on the graphs, but I'm not entirely certain on how you do that. Just trying to battle it for a little bit before the lecture, but maybe we can do it together. You guys got ideas? Oops. I don't know. I have no idea about that.
What's an application of this?
The change of variable. It's used in Bayesians quite often, where you want to move from the probability of x given y to the probability of y given x.
So what's the definition of y?
Well, the definition of y is that so you've got two variables, right?
I haven't seen the form of y.
Y is a variable. So y is,
Which is great, but how does it relate to x?
well, x is related to y, as in x's normal distribution is a function of, so the parameters of x's normal distribution are a function of y. So,
But y itself is a random variable as well, right?
yeah. So if you go to here, then the mu is a function of y. So it'll be ay plus b. So you substitute that in there. And the sigma is just, the variance is not a function of y. Right? So that's how you relate them.
Well, if you're a frequentist, you could just refuse it and say mu is not a random variable.
Okay, we're going beyond my mathematical skill here. I don't know. I think that it's kind of a condition that you're putting into your equation. You're saying that, you know, you're saying that the parameters of the normal distribution of x, or the multivariate normal of x, are a function of y. It's not, you're not questioning whether they are or not. I mean, you could pose the question.
What's the distribution of y if it's a random variable? Because it's not written on the slide. So it's kind
Well,
of
the distribution of y is here.
okay.
Yeah. So that's the whole point, is that if the distribution of x is a function of y, then the distribution of y can be related to x. So the parameters of the distribution of y are related to x. And the relationship is given to you by these a prime, which is equal to this, and so on. Does that make more sense?
So this is like if you have a normal linear function, y equals x plus 1, and then write that in terms of x just by rearranging. So essentially what we did there is the complicated rearrangement.
Exactly, yeah. So you just plug in the numbers in the original formula for what your multivariate normal distribution is, and then you can do the rearrangement. Are you still rejecting it? Or accepting it? Believing it? Disbelieving it? pretty incredible.
It looks like a lightsaber though, it's pretty cool.
That's a new one.
But it's basically just a bivariate distribution, is that just a bivariate distribution?
Bivariate distribution.
Got x and y. Is that correct?
Yeah, but x can be this long. You can have any number of parameters, so variables. So we're dealing with multivariate normal distribution, yeah? So x is not a scalar. The graphs here, they're shown for a scalar. But yeah, so the graph here is for a scalar. So you've got your x and your y, and this is how they're related, because it's a linear relationship, yeah? And now we're getting somewhere. So the linear relationship, you have the mean that goes across, and then the variance is determined by the width of the lightsaber. But it is just plugging things into your original Holy Grail equation of what the multivariate normal is. Everyone looks slightly lost.
So it's just elongated because there's a multiple possible values for the mean.
Well, it's elongated because you're not looking at x1 and x2, so you're not looking at an actual normal here. You're looking at x against y, so the two variables that are actually related by this relationship. Yeah. So the mean, yeah, it's moving along because the mean is a linear function of y. So that's why you've got a line, and the mean is in the middle, just going along. Yeah, and then your variance is a separate thing. Sort of making sense? Getting there? I think with all of this stuff, because it is essentially just getting your numbers, plugging it in, and then working through the algebra to see that these relationships are true. Probably be quite a good exercise for you guys. After the lesson. You and me. It's going to be tight. Yeah, so it's worth doing it. Or you can just take them for granted and learn how to use them. I think Gabriel would advise you to derive them. But that's pretty much it. I mean, this lecture is actually quite short. So if you have any questions, then feel free to stay behind. There'll be the two of us, unless anyone else that joins. Can you join?
Yeah.
Oh, okay. Sure. Anyway, to summarize, just an overview of some of the properties of what the normal distribution is, or the multivariate normal distribution is. And there's the list of properties. The marginal distribution of the normal is also normal. The conditional is also normal. The product is also normal, and it's normal under linear changes of variables. And there was another one. Right. Where's the other one? And under transformation of variables. Yeah. So that's it. That's your normal distribution. Now you can go into the big world and learn how to use it. Solve loads of vision problems. Thanks. You've got no more of me. You'll be happy to know. Gabriel is back on track.
What do you do actually? What kind of research?
Sorry?
What's our research field?
I do computer vision inside the human body. So I work a lot with surgery and robotic surgery. And when you're doing keyhole surgery, you always put a camera inside the body, so that's how the surgeon sees what they're operating on. And I do vision on the images from that camera.
Yeah.
You could have talked
Yeah.
about that for an hour rather than that.
Sure. Do you want to stay for another hour? It's slightly different. I mean, I do a lot more geometry, so we're very much interested in working out how human tissues move inside the body, because you've got no way of knowing it. So let's say you have a CT scan of a patient and an MRI scan of a patient, and you know where the tumor is inside the liver, and then he wants to leave and go. You're happier with the normal distribution. But when you go in there with just the camera, so you've got a very limited field of view, it's difficult to know what your targeting is. So you see the liver, you've got a tumor in it, and the surgeon kind of uses, you know, the very nice computer vision going on in their brain to align what they've observed in the CT data to what they're observing in the video, and to work out which part of your liver they're going to get rid of. Right, and that can be tricky because, for example, the liver is highly vascular, so you've got loads of blood vessels in there. And some of the things we're trying to do is, if you've got all this information, prior information, then you want to put it in the video, so you kind of do augmented reality with organs, nerves, blood vessels, tumors, and so on to help them during surgery.
So you're trying to put the images that was taken with the CD into the real life video.
Yeah, or models created from that image. But then there's other applications. So, for example, if you're using a robot, I work a lot with. We've got a few robotic systems in. We've got one clinical one in UCH and a couple of training ones, and I do a lot of work with them. So if you've got a robotic system, then potentially you can constrain the motion of the surgeon. So if using vision, if you've got this like amazing vision algorithm that can detect nerves, and then you plug that into the control system of the robot, and then no matter how good the surgeon is or what mistake they make, they cannot cut nerves. You know, the robot enforces a constraint.
You can replace the surgeon.
Well, not yet. My algorithms are not that good. I mean, they're pretty good, but just not quite there. No, the idea is never really to replace the surgeon. It's too difficult.
Yeah,
But
because
to
they would get
support.
scared and cut the funding, right?
Probably. No. It's just not practical, and also, you know, there's loads of safety issues, and you know, I mean, robotics and vision has advanced quite a lot, but it's nowhere near.
But if you like, if we have the military, we have like drones, guy somewhere remotely sitting in his clothes.
Yeah, we're trying not to blow up the patients, though. That's the
No,
thing. It's collateral damage doesn't.
It's transformational between Y and whatever it is.
Yeah, you do have slightly different things. Like the military drone just goes over there. It's like, all right, that looks cool. I'm going to blow it up.
No, but you've got a guy sitting somewhere like Delaware or somewhere.
Oh, you mean in terms of teleoperation?
Yeah.
We already do that. So the surgeon sits at a console. So the surgeon sits there, and then the patient is there, and then there's a robot holding the instruments inside. Because so everything's going towards keyhole surgery, right? So you've got these elongated instruments that are like chopsticks. And you put them inside the body, and I've got my 2 chopsticks, and then I'm looking at the screen somewhere over there and operating, and then I move down and my chopstick moves up. So your hand-eye coordination is completely reversed, right? And it's bloody difficult to do surgery that way. I mean, even if you just start playing with things on the table, it's really, really hard. And also, you're looking at everything on a 2D monitor, right? So you've got no depth perception. So you don't really have a good judgment of how far you're poking in. So you see, it's kind of a difficult thing. And if you use a robot, it becomes much easier. You can sit down, you're comfortable, you've got your nice joysticks that you've been playing with since you were 10 or whatever. No, they're slightly different. But then you've got 3D vision because you put your head in a console, and then the robot holds the instruments, and it means you've got kind of like little wrists inside the body. You've got full articulation. You don't have this chopstick effect. If your hands are shaking, the robot cancels out the tremor. You've got really magnified view. You've got motion scaling, so you move this much, the robot moves this much. So you can do everything in a really precise way. It's kind of expensive. The robot is about $1 million.
Do you have a medical background, or did you come purely
I'm
from?
an engineer.
Okay.
I'm an engineer that decided to go to surgical theatres.
Okay.
I don't know why. My sins. And then there's other stuff you can do. So you got loads of so vision. Vision using white light and webcams and so on is one type of vision. But actually, for example, different biological systems can use different spectra of light, or you combine sound with light. So you could look at, for example, exciting tissue with ultrasound.